Hello, ladies and gentlemen. Welcome to my little talk or presentation. So I wanted to do a video and give a brief overview of kind of what I'm studying. My name is Finer Stribling. I am a PhD student at the University of Texas San Antonio in the Physics Astronomy Department, and I am basically an astrophysicist. I get a lot of questions of what do I do? And so this is kind of showing you guys a brief overview, summary, or however you want to look at it, of what I do for my research and what I'm studying. So we're going to be looking at following the evolution of Messier missions and AGB stars to planetary nebula. I am going to try to simplify a lot of this terminology, and it will make more sense as we go. So before getting super in depth in the talk, I'm going to do some introductory type of information. And so I primarily big picture study stellar evolution and stellar dust. So starting off with stellar evolution, that is the life cycle that a star will take. So the evolution depends on the mass of the star. I look at masses, low to intermediate mass stars, which is 0.8 to about 8 solar masses. So for people that don't have a astrophysics or an astronomy background, solar mass, one solar mass is the size of our sun. So if a sun's a one solar mass, that means it weighs the same as our sun. If it's two solar masses, it's twice as massive as our star, so on and so forth. So an 8 solar mass star is a star that is 8 times more massive than our star. And so this is what we call a Hertzsprung-Russell diagram. And it's basically the temperature on the x-axis and the magnitude or luminosity on the y-axis. And this is kind of a chart that you can classify your stars, whether it's a B type, A type, F, M, K, M, K, G, G, K, M, and magnitude or luminosity. One luminosity star or solar luminosity is a star that's has the same luminosity as our sun. So a 10 solar luminosity star is a star that's 10 times as luminous or 10 times as bright as our star. And so the main sequence right here, that's pretty much, that's the life cycle that most stars spend the majority of their time in. And as a main sequence, you can think of it as being a star that's an adult. So pre-main sequence, you could think of it as a kid. Main sequence is its adult life. And then once it branches up to other branches, that's when it's considered evolved, late stage, or an older star. So it's our sun. This is the path that our sun was probably going to take on its lifetime. It's going to start off as main sequence. It's going to make its way up to the red giant horizontal branch, which I'll explain that a little later, up to the AGB planetary nebula, and then eventually it will continue to rapidly cool as the exposed AGB core contracts and will become a white dwarf, and it will eventually cool down until it's no longer emitting heat. And so understanding the chemistry is important to how these stars are going to evolve over time. So introducing the red giant phase, because backtrack main sequence, all stars in their core have hydrogen burning in the main sequence, but eventually that energy runs out. Eventually you run out of hydrogen to fuse, to make helium, and so you'll go into the red branch phase or red giant phase. So the red giant has a hydrogen fuel in the core runs out. So this stops the outward radiation pressure. Gravity causes the helium core to contract. The core gets hot enough to ignite a hydrogen shell. So you have a helium core. So as the core for main sequence is fusing hydrogen, the hydrogen fusion, since helium's a heavier element, as helium is created from hydrogen fusion, it goes towards the center of the core. So eventually where the core is going to become helium once you have no more hydrogen in the core. That means that the hydrogen's pushed out and you will have a hydrogen burning shell around the helium core, because the helium will be hotter, has a stronger radiation pressure. So it will ignite the helium burning shell around it, but it's no longer a part of the core. Now, because the hydrogen burning shell is going to have a higher radiation pressure, this causes the envelope of the star to expand. and it will begin to cool down to try to reach equilibrium. Now, next we have the horizontal branch. Now, the hydrogen burning shell dumps helium as to the core. Eventually, there will be enough helium in the core to create a helium flash, and that's when all the helium is ignited at once. It burns really quickly, and it causes the star to flash, quote unquote. So when that happens, the core expands, and again, it will cool down. This creates a hotter outer layer, but a smaller surface area. So that means that the star is going to make a horizontal track to the left of the HR diagram. That's why it's called the horizontal branch. So its overall luminosity will stay the same, but it will, for more or less the same, but it will increase in temperature as it comes to the left. Horizontal branch, you can see here, the helium flash happens, star comes this way, and then eventually it will get back once the star reaches somewhat equilibrium, it will start to backtrack and cool down and come up here. And that's when we have the AGB phase, or known as the asymptotic giant branch phase. So the reason why it gets its name is because this is an asymptotic path up the HR diagram, and that's why it gets the asymptotic giant branch phase. So now these stars can get up to about 1.5 AU in size, and 1 AU is the distance between the sun to the Earth. So 1.5, when our sun gets to 1.5 AU, it will engulf the Earth in its circumstellar envelope and will destroy everything, and it will get about out to Mars. So you could imagine these stars are bigger than our red giant. So they're super giants, or we just call them AGB, depending on certain variables, but just simplifying. Now, in AGB stars, we have a carbon oxygen rich core. So these stars can be oxygen rich or they can be carbon rich. But the core is inert, there's no fusion, but whether it's deemed oxygen or carbon is dependent on what's more abundant. So if there's more, so the carbon and oxygen fuse together in the core, if there's more oxygens left over, then it's oxygen rich. If there's more carbon that's abundant, then it's carbon rich. Outside of the core, we have a helium burning shell, because remember, as helium is fusing to make carbon or oxygen, that gets pushed into the center to make the core, and then the helium gets pushed out, and then we still have the hydrogen that got pushed out from earlier before, and then the rest of the AGB star is a hydrogen circumstellar envelope. Now, these stars have very strong stellar winds. They pulsate, which contributes to mass loss as well as the strong stellar winds. And these stars lose on average 10 to the -6 solar masses over their lifetime. That's the average. The mass loss rate has been known to increase over time, but on average it's 10 to the -6 solar masses. And a good point of emphasis is the maser emissions, which we talked about earlier on the first slide. Now, what are masers? Now, masers are similar to lasers. For people that don't know, laser is actually an acronym. It stands for light amplified by stimulated emissions of radiation. So a maser is basically a laser, but instead of light, or instead of visible light spectrum, it's in the microwave spectrum on the electromagnetic spectrum. So it's not visible to the human eye, but it's basically a space laser. And they're basically space lasers, and they emit in the microwave radiation. So I look specifically at oxygen-rich stars. So I'm primarily looking at silicates that are left over or that are present in these circumstellar envelopes. So the three maser emissions that I look for is SiO, silicon monoxide, H2O, water, and OH, hydroxyl. And as you can see by this diagram, I'm not looking at the aluminum based maser, but the SiO just kind of showing you, I'll explain what they are. Well, basically, they're clumps of like atoms, molecules. So the SiO molecules is a clump of SiO. And because it is a clump of SiO and it's heavily concentrated, when it emits the radiation, it's amazing. And that's how we're able to detect these molecules, because they are excited and emit microwave radiation. So now, how are they excited? Well, we get into the pumping mechanisms. We have optical pumping, which is due to photons, infrared, and then collisional or vibrational. So an example, a pumping example for optical pumping is imagine that you have a photon is the white dot and you have an atom that's the black dot. Well, if a photon's coming in from the star and it hits this atom that's in the ground state, if it absorbs the energy from that photon, it will become in an excited state. Now, if nothing else happens to this atom, and we're just looking at a single atom in a single reference frame, if nothing else happens, atoms want to try to get back to a ground state. So it will eventually emit that photon and the atom will be back in its ground state. That's just a quick example of optical. And so what we need for maser emissions is population inversion. Now, what's population inversion? Population inversion is when you have more atoms in an excited state than you do a ground state. So for example, this is what a normal distribution is. You have more, and this is for a collective group of molecules for the maser emissions. We have multiple atoms here, but more in the ground state. You have a few that are excited, and you have very, very few that are even in a higher excited state. But population inversion is when you have constant emission, absorption and emission of photons over and over in a system that are closely compact and concentrated. You can get population inversion, which is when you have more atoms in an excited state than you do in the ground state. And that's what gives us a continuous emissions of masers. Now, looking at the three different maser emissions, SIO, it's been suggested that both radiative and collisional pumping result to form these masers. So what that means is radiative is through light, whether it's an optical, a photon. Collisional pumping is very similar to the idea of the optical, but instead of a photon, it's a particle that comes in and excites the atom instead of a photon. It's the actual physical collisions. You could think of two cars crashing. It's the physical collision that excites that atom. So for a group of atoms, it's the physical collisions of dust particles within the environment that excite the molecules. So SIOs are known to be closer to the central star, about 5 to 10 AU from the central star. Water molecules, it's more suggests that collisional pumping is the mechanism more likely for H2O. H2O does have some discrepancies. It's believed that closer into 100 AU, it's collisional pumping. The further out you get to 400 AU, it might be more radiative, but primarily collisional seems to be the most dominant between the two. And OH, which are way further out from the central star, 1,000 to 10,000 AU. So remember, this means 1,000 times the distance between the sun and the earth, 1,000 times that, or 10,000 times that. Far infrared pumping, which far infrared, again, is the same as radiative because it's far infrared on the electromagnetic spectrum, which is still the same optical, it's the same optical photon, but it's far infrared instead of microwave or visible or optical for that matter. Now, moving to the next stage in the evolutionary cycle for low to intermediate mass stars, it's going to be the planetary nebula. This is the stage right after the AGB phase. So what is the planetary nebula? So the star has ejected all of its outer layers, AGB stars losing mass, but eventually its envelope will become so thin to where it's no longer, its mass has all been shed. It will lose anywhere from 40 to 80% of its mass, depending on the mass of the star. And the core of the AGB star is exposed. So as you can imagine that you have an apple, and let's say this apple pulsates, and every time it pulsates and a strong wind pushes out layers and layers of that apple, eventually you're left with the core of the apple. Now, when you have the core of the apple, there's no more reaction. Gravity wins because there's no more outward radiation pressure. So the core contracts and it creates a white dwarf at the center. Now, these white dwarfs become extremely hot, anywhere from 10,000 to 30,000 Kelvin. So that transition from 10 and at 30,000 Kelvin, it's hot enough to ionize the gas around it. Now, we do want to note that it does not become a planetary nebulae until the ionized gas starts to ionize the molecular dust or the dust around the star. That's where you get the nebula. So the transition from 10,000 to 30,000 is called the protoplanetary nebula. It's a very short time-lived phase, but that is a little preface to the planetary nebula phase. Now, the interesting thing would come with the helix nebula, as you can see here, we have the ionized gas, molecular gas, but if we're going to zoom into this square right here, we find something very interesting. These are called cometary knots. Now, they're not comets, but they get their name because they look very similar to comets because they have a nucleus and a tail. And now these images look small, they look very tiny, but these can actually be solar system size. So on the smaller side of these, they're the size of our solar system, but not particularly in the helix, they're about twice the size of our solar system. So about 40 AU in terms of size. Now these clumps are molecular hydrogen. Now the reason why that's interesting is because we have molecular material in ionized regions. Now, what is ionization? Ionization is when you have electrons being ripped off of atoms. So we don't expect molecular gases when you like molecular hydrogen is two hydrogens bonded together, H2, that's molecular hydrogen. But when you have atoms, molecular atoms in regions of very high ionization, high, let's say UV photons or X-ray photons, very, very high energy photons, then you expect those photons to come in and dissociate those atoms. Well, for some reason, these knots are able to survive these ionized regions. They're self-shielding to where they're optically thick. What optically thick means that if you can see at the head of this cometary knot, it's dark right here because light can't pass all the way through it. So that becomes very, very interesting. Where do they come from? And one thing to also note is that there's a pattern between the cometary knots. So if we back up here, they're all pointed radially outward from the central star. And then on top of that, there's also 40,000 of these cometary knots within the helix, about 40,000. So it's not like there's one or two of them that are there. It is just an anomaly. It's it's not an anomaly. It's a pattern we see across the circumference, I would say, or this inner ring of the nebula. They're on this side, they seem to be almost symmetrical in their distribution. So where do they come from when it's such a not even, but a semi-symmetrical pattern like that? Well, there are two main theories to where the origins of these cometary knots come from. One is that they form after the AGB phase through an example called Rayleigh-Taylor instability. So what happens is that you have two substances or two, let's say, gases or liquids that have two different densities. So if you can imagine this is the ionized gas, or this is just the ambient gas coming in at high velocities with a density, and you have the molecular material with a different density, where the molecular density, or something of that nature. Now, as the gas passes by, as you can see, it creates an amplified wave, and this is what plume. And as you can see, they kind of represent what we see in that cometary knot picture as the gas passes by. That's one theory, is that the ionized gas passed by, sculpted these knots, and it continued tracking out, and that's why we have tails. Another theory is that they're formed during the AGB phase. Now, if we remember, what we mentioned are the Mesa emissions. So we already have clumping that's being developed before we even get to protoplanetary nebula or the nebula phase. And the Mesa emissions actually provide the necessary density enhancement for the survivability of these clumps in high ionized regions. So that's what I primarily study. Is my hypothesis that cometary knots are formed during the AGB phase from Mesa emissions. So what I kind of did, this is a little bit ago, and I'm kind of at a different point in my research now, but what I did is I started collecting data on stellar characteristics and Mesa characteristics. So I would look at a star, look at the type of star, primarily AGB, I would get their luminosities, radial velocities, proper motion, flux, spectral type, and then I would look for their masers and look at what type of masers, how far are they from the central star, the beam size, so basically the two-dimensional size of these masers and the maser velocities. And what I started doing is I started compiling a data sheet of all these different characteristics and properties. So as you can see here, SCRT, long period variable star, or omni-set, mirror type, or this is mirror type star. Their distance, period in days, parallax, parsecs, so on and so forth. For you people that are not astrophysics background, I'll spare the details of all this stuff, but I was just keeping track of everything I could possibly keep track of. And the problem that I was facing is that it took several papers to complete one row. So there wasn't one paper that had all of this nice information that I would just write down. But for one star, I have to read a paper just to get the period. I had to read another paper to get the parallax, another paper for the flux. I have to go on databases to get their spectral types, their proper motions, stellar type, and then their Maser emission velocities, as you can see here. It was scrambling between paper and paper and paper and paper for over, I believe my sample was over hundreds of stars that I was manually archiving by hand one by one until I came across this database called Maser database. But even then, I would still have to read papers. So that's a problem I was the problem I was facing with collecting data. But what I eventually was doing for the data, or the use for the data, is I was trying to look for any correlation between any parameters. I was literally just plotting anything against everything to look for a correlation of any kind. So here I have the parallax in milliarc seconds against the luminosity of the star. And then, as you can see, R squared. So R squared is a value that we can determine for a correlation. So mathematically, if there's an R squared value, where the best fit line R squared value of, if it's over 0.5, then it's deemed as a correlation. Now, this is very, very, very weak correlation because it's 0.555. I wouldn't necessarily consider this a correlation by any stretch of the imagination. But if it was like 0.6 or 0.7 or 0.8, the closer to 1, the better. If R squared is 1, then it's basically a perfect correlation. So these are some data points and stuff I was looking, and I was just plotting literally days versus the flux. I was just plotting everything to look for correlations. And I didn't find many correlations. There were some correlations that made sense that I was finding. I believe, I don't remember specifically, but like the period in days of the pulsation, and then maybe it's mass loss rate, things like that. But there was no strong correlation that was worth noting so far. So other uses for this simulation is that this data will be used in a joint project with members from the Texas A&M Engineering Department. And they're going to we're running simulations on basically AGB star, late stage AGB star. So there's two stages of AGB stars. There's early stage, late stage. Early stage, its mass loss rate isn't as high. There's not much dust being produced. And then over time, as it's shedded more and more mass and more shells of dust, the late stage, the mass loss rate is higher. There's more dust surrounding the star. So there's different parameters, but we were primarily looking at the late stage AGB phase, and we're going to run a simulation to see if we can come up with any of we call them perturbations, but any of these clumpings or inhomogeneities that we see in the helix, in the planetary nebula. This is the Helix Nebula. I forgot to mention that. But in the Helix Nebula, see if we can produce any of these through simulations without having any Maser emissions present in the simulations. So transition, and then we just inserted, which I believe we will insert. It'll be interesting to insert Maser emissions as initial conditions, but for what we're doing right now, we did not insert information, Maser's emissions as initial conditions. We did not insert any of those. So we're going to see what happens. And then just having transition parameters for AGB to planetary nebulae. So again, we're just inserting the mass loss, and we're looking at how the dust is going to form over time. And just looking for any indications of survivability for the cometary knots. But yeah, that's kind of what I'm doing now. I'm kind of later into my research because this presentation is from a while ago. Yeah, that's all of it. But let me know if you have any questions. I might do an update video later. I probably will be getting into writing a paper myself pretty soon. But But yeah, I have questions, just comments, or reach out to me on my socials, FLS4Swag for Twitter or Instagram. Twitter's FLS_IV. Let me know what you guys think. If you have any questions, if you want to see different material. Again, I study primarily stellar evolution, stellar evolution, and stardust, how dust interacts with the star as it evolves from AGB to planetary nebulae. Thank you guys for watching, and I will catch you guys next time.